Sounds good. And I'm trying to get my sound and video optimization going. Hello, everyone. My name is Vidhani. We'll be going through the second part of optimization chapter from Kevin Murphy's book today, covering EM, expectation maximization, variation optimization, genetic algorithms, and before we jump into that, we'll go through the learning rate optimizations and learning rate schedules. So let me quickly go ahead and share my desktop, and then we'll go from there. I will stop my video share just to optimize on my bandwidth. Sometimes it's a problem on my side. Okay, does everyone see this?
Yes, we see the big screen with lots of formulas.
Right. So that's an overview of gradient descent optimization algorithms all in one page. And more than being on one page, I think it's the description that this presenter, Mazier Raisi, goes through. So there are, he has a playlist of around 600 videos, which are his lectures. He is divided into 600 short lectures. And what I'll do is I'll jump to the point where he starts talking about the different gradient descents, especially momentum onwards. It will probably be 10 minutes. Now, before we jump to that, I want to very quickly just cover this little section for the background for everyone so that we can, not this one, this other one. Okay. So this is the overall context where we define the loss functions at expectation for the data points that we have, sample we have, and the expected loss for those. And our objective is to come up with the parameters that will reduce this loss and come up with an unbiased estimate for the gradient to be able to do that, because we use a gradient parameter for that. I'll just quickly go through this because this is background knowledge that everyone hopefully knows. But if you want me to skip also, I can skip this part, but just very quickly, I can go through this also. So we have three ways to do it. The batch gradient descent, where you take the whole batch and then find the gradient at the end of the entire batch, or the stochastic gradient descent, where you go through each individual data point and find a gradient, or the mini batch, where you have a mini batch in each epoch that you go through and then update the gradients. And as has been found, SGD, which is each individual data point based gradient calculation for after loss calculation, actually makes faster progress, but then it is it's faster because of per step time is much lower. But people generally don't do that because it is waste overall in the big picture. It is waste of time computing the gradient for the repeated examples, and therefore, or even if there are no duplicates, sorry, I'm saying the opposite. The batch training can be wasteful, because if you do the entire batch and then compute the gradient, then it can be wasteful. So SGD is often faster, but it can zigzag quite a lot because each example can take the gradient in different directions. So the variance of gradient can be very high, even though it can overall converge faster or make faster progress. But the batch one is the intermediate one that people generally end up using. This is the classic equation. I'll not go through the derivation of that. People should know that. This is for the function where you have the least, the LMS is the least square, I think, least mean squares algorithm. So as you can see, if you do the SGD, the gradients, in this case, this is the weights, they can go in a direction where actually the loss can actually not even converge in the beginning, and then it can converge and come to, so this is, I think, the loss surface here. So the actual loss can actually even increase after some of the gradient updates because you're doing it for each individual data point at a time. So that brings up the other question, that what should be the step size for the gradient, and how much of the gradient should we apply, the gradient should be applied to the weight change. And that is one of the big research areas, has been a big research area. There is maybe I'll just show the curve directly. So if the learning rate is too small, so this graph that we see here is the learning rate against the loss. If the learning rate is too small, then it's kind of underfitting, and you do not see the progress happening really fast in terms of your loss reduction. If it is too high, then there's a lot of instability. So the actual learning rate is somewhere in the middle, ideal learning rate, if you may. And in order to reach this, there are various techniques adapted. There's a technique like piecewise constant learning rate. We saw this last week as well. There's an exponential decay learning rate or a polynomial decay learning rate. Oftentimes, it's polynomial decay learning rate that is used. And this is the formula for that. There are two parameters, beta and alpha, for that. Beta is the, let's see. So beta is the hyperparameter that controls the learning rate decay over time. So this is the polynomial decay, which we have here in this function on the right here. And the formula for that is over here. And alpha is the degree of the polynomial decay function. For both of those, a higher value would lead to a steeper decay. So if beta was 1 and alpha was 0.5, that is the plot that they have plotted here, I think. So beta is 1. I think somewhere they mentioned it. I don't know where it was, but with beta 1 and alpha 0.5, it becomes n0 divided by square root of 1 plus t. So beta is 1 and alpha is 0.5. So with minus 0.5, it becomes 1 over a square root of this. So that is the decay that they choose. There are other techniques where I think this one is called the learning warm-up rate. So you start from small learning rate so that you're not jumping around quite a lot. But then once you reach some values, then you can go much faster exploring that area. Maybe even potentially go to, jump the valleys as well. But once you have gone through that, that process, then you slowly want to converge to a lower learning rate and almost going down to 0. So this is a very common learning rate schedule that I've seen almost everywhere. So like learning warm up followed by cosine cool down rate. It's very, very popular. And as said here in the deep learning community, another common schedule is to quickly increase the learning rate and then gradually decrease it again. I've seen it in many papers. There's this other cyclical learning rate, which Fast AI Jeremy Howard came up with, and it discovers multiple you could say when it starts going back up, they also have a they save the parameters before they start going back up again. So there's some criteria where they essentially when you go up, you're trying to explore, and once you have found the valleys, you are trying to minimize, and then you start exploring again and minimize, and start exploring again and minimize. So the idea is that these are some local minimas in your loss surface, and oftentimes then in the final inference time, oftentimes they end up using an ensemble of these models as well, rather than just the last one that you get. So again, these are some, as you can see, this whole field is so tricky that understanding the loss surface and figuring out where which parameters fit my data and especially for out of data distribution, it can get very tricky. So generalization is very important, and all these techniques are to help with that. And then to help with the variance, gradient variance, there is iterative averaging of the parameters where you do the, so right now we're not looking at the gradient here, but just the parameters. So you do the moving average of the parameters. So there is some, like for each time t, you take only the tth portion of your parameter, but derive the most of the parameter value from the previous iterations. And this is called Polyak-Rupert averaging of parameters, very popular, it seems. There is another averaging technique where it is not time-based, but an equal averaging. And this is called stochastic weight averaging. And Polyak-Rupert is typically used in the beginning of your of your training, and stochastic weight averaging tends to be used once you have reached the flat surfaces. So if there's a lot of flatness in your objectives, then it makes it easier to rather than using the average, it helps with using equal average. Okay, so variance reduction of gradient is an important topic. I'll just skip past this one, but as you can see, this is all building towards why learning rates are important, and how, like in all of these, we are trying to figure out how to train so that we get to the minima but not jump out of it, and we do not keep going back and forth, or do not do underfitting and waste time. So that's how and why all these other these learning rate algorithms came up for optimization. So with that context, I'll jump to that video, and that will be around 10-12 minutes of video. Happy to pause for any questions at that point in time. So, and please let me know if you are hearing it fine.
The cool thing about backpropagation, I have a tutorial online. I'm not going to go through backpropagation.
We hear it. It's a little quiet.
Is that?
Is it? Yeah. So in this particular video, his volume was a little low. I apologize about that. If maybe you need to bring up your volume for now on your laptops. Sorry about that. But the next video, which is, and I'm running it at slightly faster pace at 1.25. So we should hopefully be able to do it quickly.
You can take derivatives of such functions very easily. It's very cheap to find a derivative. It's as cheap as a forward evaluation of your J function. You get the gradient of J from RD to RD. So that's what the gradient is. It's a function from RD to RD. And it's one backpropagation, and it's super fast. Some people might say stochastic gradient descent is stupid. You're just taking a gradient of your loss function, and then you take steps in that direction. That's a stupid algorithm. Why don't you use more smart algorithms? Why don't you use second order derivatives? Why don't you use Newton's method? It's second order. You need the Hessian then. And what is the problem? The problem lies in backpropagation. If you want to compute the Hessian, which is a function from RD to the matrices, because a Hessian is a matrix, you need to do D iterations of backpropagation. Then that's slow. Computing these J functions, because these are deep and wide neural networks are expensive, let alone doing it d times, and d is usually in the order of millions of parameters. That's why second order derivatives and second order algorithms are out of the picture when you do deep learning, when you do training. So we have to live with first order derivatives, only gradients, no more Hessians. So if that's the case, then how can we make gradient descent faster? There is this idea of momentum, where you say in the previous iteration, I had a velocity. I'm going to keep that velocity, multiply it by a number. Maybe I'm going to keep 90% of that velocity. That's going to give me some momentum. Then add a new gradient with our learning rate. That's going to give us the updated velocity or the new direction. And we take a step in that direction. It's as if you're rolling a ball in a valley, and then the ball, as it goes, it's going to add momentum. So this algorithm is going to make gradient descent faster, but it's a little bit careless because you might miss your minima. You might jump over it because of the momentum. You're going too fast. That's why people came up with the idea of, it's actually Nesterov who came up with the idea of Nesterov accelerated gradient. The idea is that rather than taking your derivative at the current position, look ahead before you make your decision, before you commit. What do I mean by look ahead? Forget about this part. You have theta t plus 1 is equal to theta t minus gamma vt minus 1. So you look ahead, you put that term here, that's where you evaluate your gradient, and then you make your decision, you compute the gradient. That's when you make your decision to commit. Then that's going to be your gradient, your new gradient. This is more prudent because now you're looking ahead, updating your gradient, and then adding it back to your momentum. And that's going to be your gradient descent. That's going to be the direction that you want to move towards to update your parameters. So it's always a good idea to look ahead and then decide, rather than decide and commit now and then do our actions. That's the intuition behind Nesterov accelerated gradient. So what I'm talking about in these slides are writing your compiler, which is basically, most of them are based on gradient descent. And in the deep learning literature, it's usually one of these algorithms that they use to train their models, to train their deep models. The next algorithm is AdaGrad. What is the problem with what we saw so far is that the learning rate, you have to set it yourself. You have to choose a learning rate and live with it. And usually the way that you set these parameters, usually these are called hyperparameters of our model. Whatever that has to do with the compiler is our hyperparameters. The way that you set it is usually using your validation data set. So far we talked about training data set, we talked about testing, and then the hyperparameters are going to be set using a validation subset of our data set. And the validation, you look at your, I don't know, metric, your evaluation metric, which could be your accuracy, and choose whatever learning rate that's going to give you the best accuracy on the validation data set. And once you do that, the next step is testing, and then the next step is putting your code in production. So the way that you set these lambdas, eta, is that you train for multiple times. One algorithm is grid search. You put a grid on this learning rate and then find the best one. That's the fastest, and that's giving you the most accurate result at the end of the training. And as you can see, this is not cheap because now you have to train your model thousands of times to find what is the best learning rate. it would be good if you could make the learning rate adaptive. The rest of the methods that I'm going to cover are trying to make eta adaptive, the learning rate to be adaptive. For add a grad, this is just our gradient. Let's call it G. That's our GT. The idea is that this is the same gradient descent that you have here. It's theta t plus 1 is equal to theta t minus our eta is now adaptive times the gradient. But how do you make it adaptive? You take a running average. It's not actually a running average, it's the average of the gradients multiplied by each other. So if your gradients, see your gradients could be a matrix, and the entries of that matrix are from time 1 up until the current time. That could be a matrix. We don't care about the matrix. We care about the diagonal of that matrix over time. And these are just gradients per each time. And then we are multiplying them pointwise. That's what the circle dot means. These are vectors. As you can see, the gradient is a vector in RD. It's d-dimensional. There are various ways of defining the product. Here, the product is every entry squared. That's what we're doing here. There's a square term in G. That's why you do the square root of that square term. That is trying to give us an adaptive learning rate now. And it's adapting to the previous gradients that you saw before. If we were in class, I would ask, what is the problem with this method? And can anybody answer? What is the problem with this method? Yeah, the question is, we still set an initial learning rate. That's correct. You set an initial eta, but that's going to adapt. As you go along the method, it's going to keep adapting. So this method is less sensitive to learning rate compared to gradient descent. But that's correct. You still need to set an initial learning rate. What is the other problem?
We'd have some problems like numerically when the gradient becomes really small.
That's a good point. That's why you have this epsilon term here. And this epsilon is usually set to be 10 to the power negative 8 to avoid dividing by 0. So any other problems that you see?
Is it less efficient as we continue to learn and learn because the sum over all of the taus gets longer and longer?
That's a good point. So G squared is a positive number. And you keep adding positive numbers together. So this G is going to grow. And towards the end of the training, this G is going to be very huge. It means that your learning rate is going to get smaller and smaller. And in the end, you are not optimizing at all. Basically, that term is going to be 0, and then you're going to be stuck. So the algorithm is going to stop prematurely. So what can we do to fix it? You can keep a running average rather than averaging over from time 0 up until now. You can sum the most recent gradient squares. And that's the idea of add a delta. And I'm going to say why it's called add a delta in a short while. But add a delta is going to do a running average of these gradient squares. So if you think about it, you're doing a running average. You keep gamma of the previous average, and you add your new gradient square. That's going to give you the average gradient. You do the same thing for updating. You say, this is just defining what is delta. Delta t is theta t plus 1 minus theta t. That's the definition. Nothing special there. And then you set your delta t, which is this term here, to be eta divided by your running average rather than the summation plus epsilon. The problem is that with add a delta, the units don't match. This has a different unit compared to eta. You keep a running average of your delta t. And then the update of your delta t is going to be that running average, root mean squared error, divided by the root mean squared error of gt times gt. This term here is just the root mean squared error. And that's going to be your delta t, and that's going to be adaptive at a delta. And the cool thing is that now you don't even need to set eta at all. Eta is gone. I think we are over time. If any of you want to leave, you are more than welcome to leave. And if you have questions, for those of you who have questions, you can ask questions.
You mentioned a tutorial about back propagation, and I'm interested in that. Will that be linked on the online?
I can send you the link to that tutorial to back propagation.
That'll be helpful.
I'm sorry, I think I missed it when you said it, but what's the target looking operator in Adagrad or Adagrad?
Say it again.
What is the target like operator in Adagrad, the circle with a dot inside? What does that denote?
This dot inside is element-wise product.
Okay, so it's just a dot product. Okay.
It's not a dot product, it's element-wise. So you have two vectors here, and you're multiplying them one by one. The output is still a vector, it's not a number.
Oh, the output of that's a vector.
So
Oh, I see what you're saying.
So let's
Oh,
say,
yeah. So you take it. Okay, yeah, I got it.
yes, so Blake sent us a link, and thank you, it's the Hadamard product. So you're doing point-wise operations on your vectors.
Okay, I see.
So these are element-wise squares, element-wise products. If you have x1, x2, x3 up until xn, and you have y1, y2 up until yn, you are doing x1 times y1, x2 times y2, and in the end, xn times yn. Any other questions? So there is a question in the adapt delta method, what is g squared? So g squared is exactly what you see here. Again, that's element-wise squared. If you have x1, x2 up until xn, that's your vector, then it's going to be x1 squared, x2 squared up until xn squared. The output is a vector still. So E is your expectation, is the average, is the running average, and it's just a notation. The running average of g squares at time t is equal.
I'll quickly go to the next one, which is 7-8 minutes long video. Just wanted to know, Ted and others, hopefully that was helpful. Well, sorry, Roger.
I was just saying it looks good, Dave.
Okay, I'll keep going.
Much better than what I'm doing here. And he was calling the algorithm RMS prop. Prop is for proportion, and RMS is root mean squares.
There's a question, right? Jayant, you asked if is GT a vector. So based on Hadamard product definition that he has, the element-wise product, it does seem like a vector, and that's what he has been emphasizing the whole time.
But capital GT is a scalar, right?
I think it's a vector. That's what he kept saying. Is ideally it should be a, well, see, what is theta? Theta is your parameter value, right? It's a scalar, let's say for single dimension, right?
Mm-hmm.
If you have a gradient here in gradient is also a single dimension. So yeah, it should be ideally it should be a scalar or some value like that, but he keeps emphasizing that it's a vector based on the Hadamard.
Got it.
Hey, Dave, I had to step away, but just looking at the equations that you're pointing at, they sure look like vectors to me.
GT, right?
Well, little gt is the gradient, and that's a vector.
Yes.
right? And so if you like element wise, whatever that circle dot thing, element wise multiply, then you're gonna get a vector. And if you add them up, you're gonna get a vector. So the sum of a bunch of vectors is a vector.
Mm-hmm.
Then what does it mean to take the square root of vector?
Element wise square root. It's not explicitly explained. That's not a regular square root. It's an element wise square root. So it should theoretically have like a circle around it or something.
And the summation is also element wise on those squared GRs.
That doesn't matter because vector addition is always element wise.
Yeah.
Jen, does that answer your question?
Mm-hmm. Thank you.
Okay, I'll continue.
As you can see, it's very similar. You just have a running average. Now, these are the numbers that you choose, and this is actually a good number to choose from. 0.9, 90% of your previous gradients is actually a good one. And if you look at it, it's very similar to ADA delta, but without taking the running average of delta t's. So these are a couple of adaptive methods that were introduced before Adam.
Looks like RMS prop is just at a delta with 0.9 filled in for gamma.
That's one change. Actually, for gamma, you can put it to be 0.9. And actually, in ADA delta, you put it to be 0.9. The other change is eta. For ADA delta, eta is just the root mean squared error, root mean squares of your delta thetas. So for ADA delta, you don't have to specify your eta, but here for RMS prop, you have to specify it.
Got it. Okay.
But you're right, these two methods are very similar. And the idea is generalizing ADA grad and taking care of the problems with ADA grad. Perfect. And now let's continue. Then people said the same way that you are keeping a running average of your gradient squares, you can keep a running average of your gradients. And that's going to give you some similarities with momentum. Basically, these are momentumless. ADA grad, ADA delta, and RMS prop. There is no momentum. They just have adaptive learning rates. Adam is going to introduce momentum as well. So you take a running average of your gradients and another running average of your gradient squares. These are the hyperparameters that you choose. I think one of them is 0.99, the other one is 0.999. So very numbers that are really close to 1. One advantage is that now your gradients are going to become noiseless. You're taking variance away from your data, from your gradients. The other advantage is introducing momentum, and VT is going to help you make things adaptive. The problem with MT and VT is that they are going to start with from zero. So initially during training, you're ignoring your gradients. There is bias towards 0. Because if this guy is 0, then there is a huge bias. These numbers are huge. They are close to 1. And you're basically ignoring your gradients when you start your training. That's why you have to take away your bias. So this number, 1 minus beta 1 to the power t, if t is huge towards the end of the training, this is a number less than 1 to the power of a number that's big. So that one is going to go to 0. And towards the end of the training, mt hat is just mt. Same thing for vt, because beta 2 is a number less than 1. So vt hat is just vt. But initially, these numbers are going to be close to 1, and they're going to help you give more emphasis to gt and gt squared. So it's going to unbias your estimates for the running averages. So there is a bias towards 0, you're unbiasing that. And once you do that, the rest of it is very similar to ADA grad and ADA delta and RMS prob. Instead of the gradients, you just put the moving average of your gradients. And this term is to get rid of, is actually to make your method adaptive, your learning rate adaptive. Usually a good number for eta is 10 to the power negative 3. But depending on the neural network that you have, you might change those options. So in the same paper, in the same Adam paper, this Adam paper is a paper on arXiv. And I want you to check the number of citations that it's getting, because many people are using it. That's the first method of choice for optimizing deep neural networks currently. The same paper introduced ADA-max, where rather than using the L2 norm here, this is sort of L2 norm, you can put the L infinity norm for your VTs. So this term, UT, is very similar to VT. Then you have whatever that's left from before. It's very similar to this term. And you are taking the max of whatever that you had previously and the absolute value of your gradient now. And then the rest of it is similar to what you had here. The cool thing is that now we don't have to add the epsilon, because you're always having a number that's bigger than 0. Either this number is bigger than 0 or this number is bigger than 0, and you're taking the maximum of the two. So you don't need to add the epsilon here, the epsilon term.
And to be clear, so beta 2 ut minus 1 is a vector. So is this pointwise maximization or
Exactly.
element-wise?
Yes. So this is a vector, ut minus 1. This is another vector.
And at each entry, you take the maximum in the I position of either and the maximum in the I plus first position and so on.
Exactly. So in the first position of the outcome, you're going to put the maximum of these two terms of that entry. Then the second entry, you take the maximum. That's going to give you the second entry and so on. So yeah, in deep learning, we use a lot of pointwise operations. Whenever you have your activation function, that's going to act pointwise. So most of your operations are going to be pointwise, unless I tell you it's not. So your default thought should be that it's pointwise, it's element-wise, unless the paper or the method or the code tells you otherwise. So the idea of NADAM is N stands for Nestrov. The thing is that you want to introduce Nestrov ideas and the idea of looking forward before making decisions into Adam. So Adam is like momentum. Nestrov, you need to find a way to introduce looking ahead. So you need to change this gradient. So the way that you do it is this way. So as you can see, up until this point, you have eta square root of vt plus epsilon. But now this term is trying to look ahead. So if you write down the math and if you take a look at the paper, you see the exact details of what is going on here. But the idea is you want to take a look ahead of yourself and then take a step. So there is a question from Jacob. How important is our choice of gradient descent algorithms? For instance, will Adam Max give substantially different results than RMS prop? Why am I introducing all of these methods to you? Because first, whenever you read a paper, they're gonna use one of them. Why is that? Why is there not a consensus of which method to use? Is because deep neural networks are totally different from each other. Some of them are RNN, some of them are convolutional neural networks, some of them are fully connected, and each one is gonna behave differently. That's why usually in Python frameworks that you're gonna deal with, for instance, in TensorFlow.
I'll pause this. I mean, we don't need to go through the theory that he's talking about, but essentially that covered all the optimizers he had on this page. I'm assuming this covered all of those in this as well. So we had AdaGrad, we had RMS prop and Ada delta, and then we had Adam. So I'll move to the other book in that case, unless people want to go back to the rest of the video.
Just a quick comment, Dave. So if you look at the equations, you will see that if there's a gradient or a sum of gradients or something like that, that's your S or your capital G or your whatever, you know, then that number is being used with a negative power. So it's 1 over that number or 1 over the square root of that number or something like that. That's being multiplied by your actual gradient. And so the steeper a section you're in, the bigger that number is. And so what it does is it shrinks your gradient. And if you're in a flatter section and you have a very small number, then if it's actually less than 1, then taking a negative power, it's actually going to increase it. And so the net effect, which I guess theoretically I knew, but I don't know, until like really sitting down with this and reading it, I didn't like really work out the math. So imagine you're on a valley floor or you're approaching the valley floor. You have a sort of steep gradient towards the bottom of the valley. But what you really want to do is to move very quickly along the valley floor because it's so flat that you don't want to take small steps, you want to take big steps. And that's why in the direction that has a very small gradient, you actually want to multiply it by a big number, a number more than 1, whereas you don't need to do that in the steep direction. So I don't know, that's like super obvious to everybody, but for me, it just helped reinforce what I kind of knew intuitively, but mathematically seeing it in this section.
Yeah.
Yeah, I like that. So going down the hill, you take smaller steps. On a flat surface, you make bigger steps.
Right. And then globally, you can decide if you're taking bigger or smaller steps. But the net effect, if I think you scroll up to maybe the beginning of this, I don't remember where, but basically there's a diagram in the book that shows if you have something that's sort of oval shaped, the net effect of if you multiply by like the inverse of the Hessian is that you turn it into a circular shape, so that basically your steepness is equal in all directions. Well, maybe that's not exactly the right way to say it, but basically, right, it's a circular bowl instead of a potentially very elongated bowl with a valley. And so for circular bowls, you know that you can really find a very direct route to the bottom center of the bowl.
Yeah, I don't know where that figure is. I didn't go through this book completely. Just this 8.4 section is what I did.
Yeah, that's fair. Thanks, Dave, for humoring me and covering this stuff.
No, thank you. And thank you for letting me play that video. I'm sure that person did much better job than what I could do.
It's always good to not reinvent the wheel, right?
But, as long as they're not referring to the papers from 2019 and 2022. All right. So today's topic is on section 6.5 onwards of this book. So I'll continue on this one, Ted. Any more things before we do? No, before we go. So one more thing, Ted, I wanted to connect from my iPad as well, because I think it will be really helpful if I just draw a quick diagram for Gaussian mixture model for the EM thing. So please let me in from there as well. And that will, in my opinion, help with, instead of going through just the text, going through examples will help with the understanding. And I'm just trying to figure out.
Yeah, you might need to be signed into Zoom, but it should let you in from an iPad.
So the password is Bayesian, right? Or
Capital B, yeah.
B, okay. Okay, sorry about the delay there. All right. You'd be okay if I do, does it allow me to do whiteboard, or what is the other thing where I can draw on it? Is that the whiteboard thing?
That's annotations, and once you share your screen, I believe I have annotations allowed.
Oh, it's only when I share the screen, not, so I have to share from iPad? I see, okay.
If you want to do the the annotations, yeah.
Okay, we'll see. So if I need to go to whiteboard, then I'll just go to that very quickly and come back, because it's showing me a whiteboard here on iPad, and maybe I'll use that in that case. So let's continue with this one, and we'll jump to the whiteboard for the examples for GMM to understand the EM better. So the new category of optimization in this section is the bound optimizations. So that also called MM algorithms, because you either do the maximization of your subsum function or the minimization. If it is minimization, the MM stands for majorize minimize. If it is maximization, then it's called minorize maximize. EM is what we cover in this book. There are others as well, mean shift algorithms for clustering and so on and so forth. So the key idea is that there is so the goal is to maximize some function. So let's focus on the maximize one, which is the minorize maximize example here. So the goal is to maximize some function L theta with respect to its parameters. And the basic idea is to come up with a surrogate function Q, which is actually a tight bound on this function that we are trying to maximize, such that, and the reason it's tight is in the sense that Q of theta, the theta comma theta t at any point in time is always less than or equal to the actual maximize. So it's kind of a lower bound at any point in time t, and once theta is, and at any point in time t, whatever is the maximum function is determined by this Q. So it's more or better understood with this diagram that they have, which is actually an amazing diagram right here. So the actual function in this case, let's say L, is this red function that they show here. And let's say that you have time t. So the Q is the surrogate function that they have here in blue here. And the maximum Q theta t, so Q of theta at different theta is always less than. So if I look at this point, it is less than the actual value of the function, but the place where it is maximum is theta t, and that's what it is trying to say over there. Let me just go back there. That Q of theta comma theta t is always the this L function is the bound, so it's always less than equal to L theta, but at theta t, this is equal to L theta t. And the objective is to find that theta. So we need to, so once these conditions are met, it's called Q minorizes L, and then we're performing the update so that the next theta t is now the maximum, the theta that maximizes Q. And again, going back to the picture. So for this blue line, the next theta is theta t plus 1, because that's where this function Q is maximized. And that becomes our next theta t. And then in the next step, to go to theta t plus 2, as you can see, this is the green function that is the Q for that time step. And it is always a lower bound. So for any theta other than theta t plus 1, the green function is smaller than then you find this function Q, and then you keep moving forward. At each time step, you're coming up with these surrogate functions, the blue line or the green lines, which are slowly taking you closer towards the maximum of your red function. So that is a key idea that you'll see being described. So there are some deductions that they have, how and why this Q is for each time step is monotonically increasing towards the maximum value. I'll skip past those, but people interested can read that. But the main idea is what I described in that picture there. So before I move forward, any question, let me know. Otherwise, I'll keep going. Or any discussion points.
So Dave, in the 1D picture that you showed, I think of this Q function as something that's tangent underneath our actual red function.
At t, right? Yeah.
Yeah, it has to touch at the point t.
Yes, that's the maximization. So so that's also a very good point. So in some ways you can say that this is up. I mean, if it's a if it's an equation that can be easily solved, and you can potentially use the Lagrangian multiplier to find that tangent, and see that you could have many Qs here, right? You could have any Q that you choose from, but you have to choose Q that is the tangent, but you have to choose some function so that theta plus 1 takes you to the higher value of the L function in the next step. So I don't want a tangent where, well, if it is a tangent, a delta theta, like, just moving a little forward will take you a little higher, but you want to maximize that so that you move.
No. I'm not talking about the slope. I'm not talking about the gradient. I'm simply saying that because this is a tight lower bound, it can't just be blue somewhere way below the red curve. It has to actually touch it. It has to equal it at that one point.
Yes, that's true,
right?
Because you find it this way: Q theta T theta T is the
right. So if you didn't have it be tight, if it was just way below, it could wander around and still be below the red curve and not necessarily be quickly approaching the maximum of the red curve. You know
I
what I'm
think
saying?
by changing the parameters in theta,
So I'm not 100% sure of that, because what if you have a square function, like, just a, what do you call it, the step function, right?
Mhm.
So it could be a non-continuous gradient there, right? So it just touches it and then moves right. I mean, it still satisfies that, but then you may get stuck. So in some sense, there could be many functions that can satisfy this.
Oh yeah, there definitely could be many functions, but what I'm saying is that on your blue curve, you can see the point where it touches, right? That's called theta t. And then the point slightly to the right of it, not all the way where the green is, but just slightly to the right of it, theta t plus 1 is the highest point on the blue curve. Okay? I'm saying if blue was not a tight lower bound and it was way below red, it could be any shape such that the highest point on the blue curve could have been to the left of theta t.
Right. If it came from here, for example. If you
No. I'm saying if you shifted the blue down halfway.
Oh yeah, that's what you're saying.
And it wasn't a tight bound, it could be any shape it wanted.
Yeah.
Mhm.
And so then when you maximize blue, you could be wandering around in the desert. And remember, this is just a one-dimensional thing, so you can't wander that much. But in a multi-dimensional world, you could just be wandering around in the desert lost forever, for a long time, right? By forcing blue to be a tight lower bound, now when you maximize blue, you actually are moving up, so to speak, on the red as well.
Right.
Does that make sense?
Yeah.
Just trying to speak to like the intuition of why, right? Moving up on blue works if it's a tight lower bound. If it weren't required to be tight, it would not be as helpful.
Right.
Right? You might be able to prove that you couldn't infinitely wander, but that doesn't really do you any good. You want fast convergence.
So another question then, we know the function L function, the red line function, right? So the reason we are doing this expectation maximization is like, is it costly to evaluate this red line function, or we cannot get derivatives of it? What's the reasoning behind, and how do we guarantee that it's always upper bound to the blue line?
That's right. You only do this when you don't really know exactly what the red looks like, and so you're just trying to so like when we do gradient descent with a neural network, right? We don't know where the lowest loss is.
Yeah.
We're just trying to
Explore.
iteratively find our way closer.
Thank you.
Yep. Thanks, Ted. So as you said, could be lost as well. So if let's say you were over here at this point, and if the red function has multi-modes, right, then it is potentially possible that you are lost as well. So that's where there will be other techniques that they'll discuss about this.
Yeah. If your red function is not convex, then there's no guarantee you find the global maximum. You will find a maximum, a local maximum.
Yes. So this is an example that they took here where they are trying to, there's logistic regression where, so if L theta is a concave function, in this example, they had this as a concave function, right? Concave function, and you want to maximize, then one way to obtain a valid lower bound is to use a bound on its Hessian. Calculating Hessian is very compute intensive. So finding a lower bound is a good way to estimate it. And that's what then many of the approaches to that. In this case, they have so if you have that, then you can estimate your next value of the parameter by using your Newton update method. So you would see that many of the future discussions are focused on finding that lower bound on Hessian. This is an example of linear regression, right? We're looking at, and in a case of a n class example where you have classes 1 to C, and the probability that your nth element is y given your input xn for nth element and the weights. This is the probability that is for assigned for that, and so this is the binary. In case of this is C classes. Just like binary logistic regression, you need one less parameter. So I mean, that's irrelevant. Essentially, talking about how to model this loss in this case. So for classes C to C-1, and the reason they have C-1 is because the last category's probability is automatically known once you have n-1 probabilities known, that they all sum up to 1. So for the categorical logistic regression, you have the following function that you want to maximize, or in this case, the negative of this is what you want to maximize, the log likelihood. And the Hessian for that looks like for that example looks something like this. However, this can be very intense compute intensive, and then literature is there to show that there is a bound on Hessian, which is actually pretty straightforward bound, something like I think, where is that bound shown? I think this is the bound, -1/4 for x transpose x, where x is your data point. And yeah, this is, so we found our B, and essentially you have only one single matrix to work with rather than different Hessians at different points, and then you keep on optimizing your W based on this one matrix lower bound, and find your approximate your parameter for which the Mac function will be maximized, in this case the negative log likelihood. Okay, so we'll come to the expectation max. So that was the introduction to single dimension simple example. Now in that case we had all the variables and data known, but in case of the places where EM is applied is when there is missing data or there are hidden variables. And a very common example is the clustering algorithm, where clustering problem where you have a set of data points that are given to you, and you want to find out what clusters they belong to. So let's say you have five clusters that you know upfront, but the data points are spread all over in your even 1D for that matter, one-dimensional problem. You don't know where these points belong to, which cluster those points belong to. And the expectation maximization algorithms help you solve for that, whether it is k-means or whether it is mixture of Gaussian mixture model. So it all and in case of clustering, when you have n points, the hidden variable for those endpoints in k-means is the centroid for those points that are part of the cluster. And in case of Gaussian mixture, it is the Gaussian parameters for each of those points. And maybe it's probably best explained if I switch to the whiteboard, and then I'll quickly come back to this, but it is just to give the motivation for how expectation maximization will work.
All right, so Dave, we've got a little over 10 minutes, so I don't know how much time you want to spend on the visualization. Happy for you to do it, but just you know,
maybe 2 minutes just to kind of get that going very quickly.
Okay.
And it says I cannot do it if I'm already doing screen share, so I have to stop share and come back. You have to, someone has to give me permission on this other iPad as well.
I think you should be able to now, Dave. Sorry.
Yeah, do you see it now?
Zoom whiteboards are weird. Just because you're doing one doesn't mean you're sharing. Can you share your screen now that you're in the whiteboard? Now it seems like it's coming up.
Okay. Okay.
Yeah, I see communicate with comments.
Yeah, but I don't know how to get past this. I thought whiteboard will be very easy to use. If it's not, then I'll just go back and assume, try to talk through it. A picture is worth way more than the words I'll speak. So I thought I'll just quickly do this and then jump to that.
I can see the whiteboard.
Yeah, but I'm not able to use my pen on it.
I don't know. I played with whiteboard once, got it to work, but like when I'm in a pinch, I just resort to something super crude like Microsoft Paint, and I can draw things.
Okay, let me do that then. Maybe that is an easier way to do it. Good idea. And let me share my. I apologize if it is causing more problems for the meeting. Okay. Okay, so consider, on a you have a set of points that you want to find, put the clusters around, find the clusters for these points. One way to, and let's say you want to make 5 clusters for it. One could say that maybe one cluster is this, and you want to give the distribution for the weight for the clusters, meaning how probable is each cluster going to happen given these data points. Let's say the other cluster is this, the distribution of the points. So, and then let me maybe in order to qualify that a little bit more. So let's say this is my one cluster, this is my other cluster, this is my third cluster, this is my fourth cluster, and this is my fifth cluster. So you could say that, well, for this first cluster, it is centered more towards here, and centered more towards here, and the variance is this much. The second cluster is centered more towards here, and this is the variance. Let me remove this. The third cluster is centered somewhere here, and this is the variance for the data points to be part of that cluster, and so on and so forth. This is my fourth cluster. This is the center, the mu of this cluster, and this is the center of this cluster, and this is the variance. What do I mean by cluster and variance here is that the mean and variance here is that for this cluster, the mean of all these red points is this value, and the points may belong, given that this red point belongs to this cluster, and this red point also belongs to this cluster. The distribution of data points belonging to this is something like this with a lower variance, and this is the mean. However, for let's say this cluster over here, this is how my distribution for data points would look like. If I have to put one probability distribution for all of these points that I see over here, the probability distribution for for all these points would look something like maybe like this. This is how the data points are distributed. But when I put them in clusters, then I would say, well, with the probability that this point here belongs to this cluster is determined by the Gaussian distribution for that cluster for the points. But then this point could also potentially belong to the cluster 2 here, but even though it may have a lower probability, but there is a probability given where this point red stood that it can belong to this cluster or this cluster. It could potentially belong to even this cluster with a very, very low probability. And if I messed up the picture by now, but the point is to kind of help understand that the points that you're trying to cluster, a new red point that you have, let's say over here, it could potentially belong to this cluster or even this cluster for that matter, with maybe with almost equal probability to this cluster on the left and this cluster on the right, and with a lower probability to this cluster on this right, or even lower probability to the clusters on the far right. And the objective of this clustering through the expectation maximization algorithm is to find for these 5 clusters, what are the means and the variance for each of the clusters, and what is the probability of occurrence of each of the individual clusters. The assignment of each point to a cluster is called the expectation step, and finding the parameters for each of the Gaussian curves for the distribution is the maximization step. And as you would see when we go through that this is done in iterations. In the first iteration, you potentially randomly assign some mean and variance, and you assign every point to some random cluster. Based on that, you get, for that particular cluster, you have 5 clusters. So you assign each point to one of the clusters. And based on that, you have some likelihood mean and variance for that. That will maximize the assignment. And that's called the maximization step. Now that you have the assignments done, you move to the next step to reassign the points to the clusters, those 5 clusters, so that it will maximize your expectation for those cluster assignment. Once you have the cluster assignment in the second step, you again move to the maximization of your parameters for each of the clusters, their mean and variance. So that's the iteration that happens. And I'll go through the text, but this is what happens in expectation maximization. And I don't know if I did a good job, but just wanted to go through this example because that's the classic example for for expectation maximization. But you're right, Ted, it is 7:27. I mean, whatever you prefer, I can go through that. I can go through the rest of the EM section, or we can do it next time, whatever you recommend.
Yeah, I think maybe next time, and I hate to do this, Dave, but I have an obligation to do my referee job. Okay. So unfortunately, there's just too much material in this book, and we can't teach it all because it's 1,200 pages. We'll never get through the book. So if you're willing to continue with chapter 6 next week, I'd love it, because I do not want to try to lead the discussion on optimal transport. I'm really hoping you'll do that. But what we need to do is try to find this balance where we cover the topics, we see if people have questions, if maybe there's a little bit of discussion around intuition or whatever, but unfortunately, we just cannot take the time to deeply walk through and explain, like, I thought today was really great, but like, we can't go through all the optimizers, and we can't go through, Gaussian mixture model when, there's just so much material.
Right. So how about this? Let me just finish this EM chapter very quickly, this section, because it will just take 3-4 minutes, honestly, because that was the idea, to just introduce it. I'm not going to go through the equations. Let's just go through that, and you can put a pause and let me know whenever you think that that's too much.
Okay. If you really think you can do it in just a couple minutes.
Sure, it will be.
You said a couple minutes for the drawing, and that was 10 minutes, just so you know.
Yeah. Okay, let's do that. So I like your point there. Okay, so going back to that one. So here we are. So this is the function that we want to maximize. Probability of each of these values that we saw, but there are some hidden variables z that we are trying to also find the parameters for us along the way. We translate or transform this function so that it, using the Jensen's inequality, it changes to, we found the lower bound on it, which we call the evidence lower bound in this case, by using these transformations. But along the way, what we have done is to define Qn, which is the distribution for these z's that we are estimating over here. So essentially, our function has become now a parameter of theta and Qn for the data set that we have. And the E step tries to optimize on the Q, which is the distribution for the z's, and the M step tries to optimize on theta, and you iterate between those of two. First, optimize on the distribution. You get some values of z. Based on that, you have the function, and then you optimize on theta. Based on that, you have the new estimate that you want to make for your z's. So you come up with the new q, and so on and so forth. So that's the iteration that you have in the E step and the M step. So that's what the expectation maximization is. So as I said, in the E step, you'll find the Qs, which will lead you to find the Zs, and then in the M step, you find the parameters for your hidden variables. I'm not going to go through the example because my idea was to go through the Gaussian example, which I already did. And then that's what it was in this section. So sometimes there could be an issue where variational expectation, I forgot about this one, but from the picture, what I recall is that sometimes, so you're trying to maximize the likelihood in your second step, in the M step, but because it's continuously increasing, sometimes you may have, and you're never close to that peak sometimes you may cross that peak, and and you may never reach the maximum likelihood point. So this is what this example is saying, that when you're trying to find this function that maximizes your likelihood, but it's an estimate, and you may sometimes go past it as well in the in this thing. The M's, I'll just go past. So then there are some other mechanisms they have for the EM part. Sometimes you just fix to the maximum value of Z rather than finding the distribution, but then that can lead to overfitting. You have Monte Carlo EM, where you sample and then you compare the values that you found, and based on that you do the stochastic approximation. GEM is another one, and the ECM is when the parameters are dependent on each other. So there are algorithms to handle all of those. And then online EM is when you are updating your parameters based on new data that is coming in. So that's your EM.
All right. Thanks, Dave. Thanks for going through that quickly. So are you going to be here next week? Are you game for trying to finish chapter 6?
Yeah, I can do that. No videos, but just presentations.
Yeah, and scanning over it, I don't know that we need any of the stuff in the rest of the chapter super heavily for what we're likely to see in the rest of the book. I think optimal transport theory may underlie a lot of things, but I don't know that we're gonna, I could be wrong, but I don't know that we're gonna really hit it hard in future chapters.
So the only time where it is becoming really popular are a couple of places. One is in the VQ side. You will see that when they quantize it, then they need to figure out how to assign the probabilities for the quantized values. The other side is on the diffusion side. So we'll see that for sure. The new algorithms are leveraging optimal transport. And then the other one on the evolutionary algorithms, they refer to a lot of forward reference basically to reinforcement learning. So several places, both on Bayesian optimization and evolutionary algorithms have forward reference to RL quite a lot. So again, majority of these sections are interleaving. So there are a lot of forward references. So I'm assuming when we go through those, there will be backward references again. So
yep, exactly. So we can always touch up on stuff if we feel it's necessary. All right. So then the game plan is going to be next week we finish chapter 6, which means we actually are going to finish part 1. So we will be done with the foundations, and then we can actually start on Bayesian inference. And the goal is to try to finish Bayesian inference before we get to the summer. If people are sticking around, or if they're online, then we can talk about do part 3 over the summer, and then part 4, I believe, is like generative models, which I'm really hoping we can do in the fall, because that's where all the hype seems to be these days, right? It's either image generation or chat text generation. Super, super duper hype.
yeah.
All right. Thanks, Dave.
Thank you everyone for staying through this.